Okay, I think we will start. So hi everyone. I'm very happy to have in the ACRC webinar Professor Boris Murmann from Stanford. Boris gave a memorable course 8 years ago, but unfortunately now he can't give this course at the Technion. So with the limited resources we are now in the condition, we are happy to have him for this webinar. So Boris, the floor is yours.
Thank you, Shahar, and thanks everyone for calling in. I'm very honored by this large attendance. So today I want to share with you what my group is doing in the space of mixed signal computing for deep neural network inference. For those who don't know me, for those who don't know me, I'm running a relatively large group working on general mixed signal design. We touch almost everything in mixed signal design. So we build interfaces to physical analog sensors. We're trying to push the state of the art in sensitivity. For many of these applications, we're building A to D, D to A converters. And more recently, we have discovered that it's actually important to think more about algorithms. We worked on calibration for data converters, and that sort of got us into this field. And now neural networks are a very interesting topic, and looking at how they synergize with the kinds of skills that we have from the mixed signal design space. So what motivates most of us when we talk about this? Well, you know, the Intel CEO even said it, data is the new oil. This is really what's driving a lot of progress and innovation now, is the higher levels of abstraction. And specifically about deep learning is that it actually thrives on data. So this is a very famous chart that kind of shows this breakthrough event when people realize that the more data you feed into deep neural networks, the better the algorithms perform, and they actually outperform older algorithms that were mostly hand engineered. So this was a very significant event, and so perhaps sometime around 2012 or 2010 or so, depending on how you think about it, is when this whole deep learning hype took off. So at the same time, as I said, this field thrives on data. We actually have the data now. This is one of the very important ingredients of this trend and why people care so much about it. So the amount of data that we create is still exponentially growing. And if you plot this on a linear scale, it almost looks like we didn't have any data before, say, 2008-9. But we're measuring this in exabytes, and it just keeps going up and up and up. And a lot of this data is what people call unstructured. It's emails, raw audio, images, video, sensor data. And we would like to interpret what is in this data, what does it represent, using these deep neural networks. And so this has become a huge field, and it's not going to go away anytime soon. There's a lot of exciting developments on both the algorithms and the circuits. So in a nutshell, really what we're doing is we're collecting large amounts of data, and then we're building machine learning algorithms that try to make sense of this data and perform some kind of inference. You know, there's the famous cat-dog example. You know, am I seeing a cat, a dog? Is someone saying, hey, Google, and so on. So there's an endless list of things that we do on these data. And all of it then revolves around devising the right machine learning algorithms, minimizing their footprint, training them properly, and so on. So in this presentation, I will not talk much about training at all, which is an art in itself. In fact, training is probably even more difficult than thinking about inference. But for hardware, it's actually interesting to make this inference step very low energy so that you can deploy it in small devices and so on. So I'm going to be talking about what kind of hardware innovations we can make to make this inference step as low energy as possible. So moving a little bit in that direction, what are the architectures that people use for these machine learning algorithms? So definitely today's workhorse, even though there's other algorithms, are deep convolutional neural networks. And this is a nice drawing that Vivian Z made. And this essentially applies to classifying images here as an example. So you take an input image, And what you do is you run filters across this image, and you look layer by layer for correlations with patterns within these filters. And so you run them stride by stride across these images, you measure the correlations, you apply some nonlinearities, you normalize, and so on. And you move from low-level features to mid-level features to high-level features, all the way to the point where you can take a fully connected layer or some softmax classifier to then give an output score. For example, is this a dog, a cat? Is the word yes, no, or hello, or something like this? So this is computationally extremely intensive. And this is not surprising, because a lot of these classifications are relatively subtle. And so people have worked on making the algorithms more and more efficient, reducing the number of layers as much as possible, or making the layers as compact as possible and having many layers. There's many ways you can get an efficient network. And here's a snapshot of where people stand with these network optimizations. This is absolutely not my field, but I look at it mostly from the perspective of, well, what are the requirements from the hardware? So on the x-axis, you see here how many multiply accumulates are needed to execute one inference step through a convolutional neural network. And you see this is somewhere in the billions. So 1 to 10 billion is a reasonable range. And so people try to push these points in the upper left corner here, make the number of computations as small as possible, and make the inference accuracy here, using the ImageNet database as an example, as high as possible. And so this is an entire field by itself. Model compression, how do you prune these networks? Can you remove redundant weights? How can you aggressively quantize? Maybe I can get by with 2-3 bits in these computations. Look at sparsity. Not all the signals are moving all the time. Can I somehow take advantage of this? Can I decompose these layers into more compact structure? I have an example at the end, and so on. But this is an enormous field, and it's sort of running in parallel to the whole hardware development that I'm talking about right now. Also related to this is the quantization aspect. I hinted that already. It turns out for inference, you actually get by with relatively small bit width. 8-bit tends to be sufficient for almost anything. And if you have clever tricks for training, you can even go to 1, 2, or 3 bits in the computation of these convolutions. And so this is a very nice chart from folks at IBM that actually showed that when you look at this as a Pareto front, where you have the model size versus accuracy, and then you look at different options for the precision in the computations, you often find that 2 and 3 bits are actually at the Pareto optimal when you consider model size versus accuracy. Nonetheless, of course, when you build a server processor that wants to be general, you may still go with 8 bits so that you're not customizing too much. But when you try to minimize the inference energy as much as possible for a mobile device or a small sensor device, you will ultimately maybe go to 2, 3, or 4 bits to minimize the footprint of the network as much as possible. So let's look at some of the numbers. So what do I want from my hardware? So clearly I want small power dissipation, and power is the rate at which you do the computations times the energy per that operation, which is an inference. So this is actually the ultimate metric. So if you want to look at an application and a specific classification problem, you ultimately want to reduce the energy per inference. Now, it's important to realize that has 2 components. Energy per inference is how many operations you have per inference, and then the energy per these operations. So both are knobs that you can turn. And the architecture community is trying to turn this blue knob. They're trying to make less operations per inference necessary by compressing the models, exploiting sparsity, and so on. And in my camp, in the hardware camp, we're trying to reduce the energy per operation, which is mostly multiply and add. So if you had to formulate a dream, you know, if you want to have a piece of hardware that would work really well for state-of-the-art examples that classify ImageNet complexity type problems, you would like to do something like 10 gigaops at around some tens of milliseconds. So you have on the order of 1 teraop per second for a reasonably sophisticated neural network. And then if you really want to run this on a small battery, I'm not saying this exists, but if I had a dream, I would want this 1 teraop at 1 milliwatt. So this is 1,000 tops per watt, and it corresponds to 1 femtojoule per op, which is just the inverse. And so this is kind of the dream, I would say, that people are chasing. And I'm going to show you how close we are to this dream and what kinds of steps we should take to get closer to this. So this is really just to give you a feel for the numbers. So let's now zoom in and let's look more at the operations that we have to perform. So these convolutional neural networks, they're complicated beasts. There's a lot of bells and whistles and a lot of interesting operations. There are these nonlinearities. There's max pooling. There's all kinds of intricate operations that go into these. But by far, the one operation that consumes the most compute horsepower is just the basic convolution that happens in each layer. And so this is what I'm trying to illustrate here. So you essentially take a volume of input data. These are called input activations. And you take a filter volume. This is this blue volume. And you basically move this around in this input data. And for every position, you perform a dot product between this red volume and this blue volume. And you get exactly 1 output pixel in the output volume. So there's actually massive parallelism. You have a lot of multiply adds per 1 output piece of data. And so as you move this filter left and right in the input volume, so does this output pixel location. And so how do you cover this dimension k? Well, you have k of these filters. So there's a lot of filters, and they all slide through this volume, and they fill up this output volume. So many multiply add, billions of multiply add need to be performed total across the whole network. So clearly, this is, you know, computer architects call this embarrassingly parallel because so many things happen in parallel, and that you can exploit by building the hardware with some parallelism. And more importantly, there's also data reuse. So when you fetch the filter weights from memory, for example, you can keep them locally for a while until all these convolutions are exhausted, and then you fetch new weights. So this is what's meant by reuse. You could also reuse partial products from previous calculations. If you stride the filter by 1 to the right, you can reuse some of the previous multiplications. So this in itself is a very interesting optimization problem that has been beaten to death in the last 10 years. There's a lot of interesting papers about this. So all of these findings have led to very nice DNN chips that people have built. And so I'm looking now at the typical architecture of a fully digital DNN accelerator. Oftentimes, you have a piece of DRAM on the outside, because if you want to have 10 or even 100 megabytes of weights, it's very hard to put that on a chip unless you have a special technology. And so typically you have a hierarchy that starts with DRAM, and then you have buffers of decreasing size. And these buffers are managed in a way that essentially exploits this data reuse that I talked in the previous slide. So when you fetch a filter weight from the DRAM, you keep this weight in these local caches for some time until its usefulness expires. So this is a very interesting scheduling problem. How do you schedule the computation, and how do you move the data, and so on? And so this has been figured out over time. There's some interesting frameworks that give you the optimum architecture and schedule. So one thing that's interesting to note is that obviously the access energy of these memories is vastly different. For DRAM, you may pay up to 10 picojoules per bit that you fetch. For smaller buffers, it's single-digit picojoule. Then you go into the femtojoules for smaller SRAMs, and then tens of femtojoules for very small register files. And so across this hierarchy, it turns out that if you do a good job in designing these accelerators, the energy is actually somewhat evenly distributed across these memory accesses. This is what you would expect from an optimal system. None of these levels should dominate too much. So here's an example of a very nice digital accelerator published by NVIDIA. This is a Journal of Solid-State Circuits paper from a couple of months back. So here you see this processing element array. They have 16 of these processing elements, and here's a global buffer, GB. And then inside these processing arrays, they really have mainly these multiply accumulate units. So this is a vector MAC as they label it here. And then inside, they have these accumulation buffers where they just keep accumulating the multiplies. Remember, we have to dot product these entire volumes. And so you keep adding to this final output value. And this happens by writing on this accumulation buffer. And so you build many of these to have parallelism. And then you keep certain things stationary within each PE. In this case, they decided for what's called a weight stationary architecture. They actually keep the weights within each PE stationary as long as possible, and then they move in new weights, and then they perform a bunch of computations and so on. So this is very cleverly engineered, and this sort of gives you the state-of-the-art performance. When you look at where the energy goes in these PEs, and again, the PE energy is then a very significant fraction of the overall energy if the system is optimized right. A lot of the energy obviously goes into the compute, so you see that's 31%. But interestingly, and this is also very important for people who want to go into this space, is to realize that no matter how you look at it, even the local memory accesses are a very big deal. So if you were to only improve the compute by itself, you would have a very limited impact on the overall neural network, because really writing into these local buffers, regardless of how you architect the PE, there's other architectures, you end up hitting these register files or accumulation buffers very often per computation. And so it turns out that the memory access, even at the local level, tends to dominate. So what we shouldn't do as analog and mixed signal designers is to say, well, you know, I'm going to keep the same architecture. I'm just going to drop a little bit of better computing in here and I'm done. Well, you wouldn't really gain much of a benefit, because that's a small piece of the power of a pie. It's a reasonable size of the pie, but it wouldn't propel you by orders of magnitude. So this is one of the important messages here when you look at digital accelerators. So what am I proposing? Really, I'm proposing to introduce a little bit of a different scheme or new degree of freedom that may allow us to get to less memory access overhead at various levels, at the various levels of caching. And of course, we also have to reduce the compute energy. But the key message is it's not only reducing the compute energy. So this is a very high-level cartoon. I will concretize this quite a bit in the following slides. The conventional digital architecture that we just looked at looks a little bit like this. You have tens to hundreds of these PEs. They have this hierarchical memory architecture. You have quite a bit of memory within each PE that gets hit quite frequently for each computation. And this really sets a ceiling on how efficient you can be. Now, the mixed signal accelerators that I describe have a little bit of a different philosophy and have a more interspersed architecture where you have much more parallelism and local memory associated with these parallel computations. So the different colors, as I'll concretize this again. So analog compute means mostly accumulation. There could be analog memory like RRAM memristors and so on that you can toss in there that could be beneficial for density and other reasons. And so just sort of giving yourself the functionality that you get out of a mixed signal fabric and seeing how that affects the overall solution is actually an interesting topic to pursue. So let's dive into more details. So this is admittedly a pretty complicated diagram, but let me explain it step by step. It's basically an expansion of the simple cartoon that I just showed. So the idea is to make an array of relatively simple unit elements. And so this is this gray box here. So each unit element has some weight memory. It could be one word, it could be more. This is really up to the designer. There's some multiplication, and then there's an addition. These are the core operations for these convolutional layers. And so what's different from the digital architecture is, one, we're trying to make these relatively dense. And then two, we're going to do basically spatial accumulation between all of these cells in the analog domain. So think of this as charge or current summing. I will put circuits to this pretty soon. So the result is that you don't have any of these big adders or buffers that sort of capture these multiplications that have large access energies and so on. You basically just want to use wires to get addition. So this is one of the key advantages of doing analog. So the weights are kept stationary. So the most suitable data flow for this is a weight stationary one. And so you want to make sure that this array is large enough so that you don't have to reload the weights very often, because that again would give you a lot of energy access overhead. So you want to make these cells very small so that you can load the weights and have large arrays and keep these weights there for as long as possible. So what's nice about having a large array also is that when you fetch input activations from the buffer memory, that memory access gets amortized across many, many columns potentially, because this fabric is very dense. And so the access energy from this buffer basically relatively in the overall pie chart of the system goes down versus the compute, and this is very much desired. Now, the problem, though this is all very beautiful, the problem really comes in when you want to go back now to digital. Some people advocate that you shouldn't do this or something. I still think that regeneration is actually possible in VLSI. So you will, after this accumulation, typically neural networks will have to do a bias. You can also do some batch normalization parameters here, but this is beyond the scope of this talk. And then you do A to D conversion. And now A to D conversion, just like memory access, is actually expensive. And so you will also have to make sure that you have plenty of rows over which you amortize this ADC. Oftentimes, what you want to do really is to have as many rows as your largest filter kernel. So think of this blue volume to be unrolled into the number of columns that you have here. And ideally, you want to unroll this entire red kernel into the maximum number of columns that you want in your set of kernels. So this is essentially the setup. Let's now look a little bit more at these two aspects of amortization. So for ADCs, of course, I've been working on this forever, so I have some reasonable idea of what energies you can get. For these neural networks, you have relatively low fidelity, so you will have something like 4 to 8 or 10-bit ADCs. We'll talk a little bit more about this. So you see you're sort of sub-picojoule with these per conversion. So if you think about our earlier calculation, if you have to expend a picojoule for the A to D conversion, you better amortize over more than 100 rows or so to get down to 10 femtojoule per Mach, which is a reasonable range to be in to be competitive with the latest digital, which, by the way, is close to about 100 femtojoule per Mach. So this gives you an idea of array size in the Y direction. In the X direction, here's a nice example from the previous ISSCC, kind of showing you what happens when your array is too small. These folks built 64 by 64 compute arrays. That's what these CIM macros are. And so you basically, when you do 64 by 64, since the network dimensions are much, much larger, or let's say the kernel dimensions within a layer are much larger than this, you constantly have to reload weights and you constantly have to broadcast in new activations. So the efficiency of this array alone, without counting for the buffer, is 158 TOPS per watt. But when you include the buffer energy, it drops to 35. And so this is one of these gotchas. If you go and build compute arrays that have a weight stationary flow, You can't make them 10 by 10 or something. There's no utility to this because feeding these small arrays from the outside will overwhelm the efficiency of the whole computation. So this sort of the main ideas and concepts that we have to watch now. I really want to go into circuits that we have built and other people have built to kind of give you a lay of the land into how far this has advanced. So we started out kind of building reasonable sized networks around 2015, and it took us really about 3 years to figure out what to do and how to execute it. And so our first network that we built in this style was a BinaryNet. That came out at the time as a very interesting option. People had figured out how to train neural network with single bit weights and activations. And what's nice about this is that this multiplier in each unit element just becomes an XNOR. And the addition we performed by charge sharing between capacitors across the column. So in principle, this is actually very area efficient. It turns out to be also very energy efficient since you can make these capacitors small, order 1 femtofarad or less. And so 1 femtofarad, you know, if you switch that, it's 1 femtojoule. You're kind of getting into the regions that we talked about in the beginning. So here we made this array reasonably large, right, to amortize well. So this has 1024 rows and 64 columns. This is what we could fit on our academic chip at the time. We made this into unit elements that looked like this. And in retrospect, this wasn't really the densest solution. It was something that we could do relatively quickly, you know, and when you do something for the first time, it's never optimal. We used a latch for the memory cell, which is also not the smallest option you can think of. We used differential signaling because we were scared of coupling noise and so on. This is also, in retrospect, probably something we wouldn't have needed. And you know, here you see these capacitors. So overall, you know, while these cells were reasonably small, there's denser solutions now that I will show you a little bit later. But in the end, this led to a complete chip where this array of 1024 by 64 is in the core. This is what we call this neuron array. So you could call this 64 neurons with 1024 synapses each if you wanted to use that nomenclature. And this was really one of the first mixed signal neural network chips that has images in, labels out. So this is really a complete system. And I can only encourage you to go in this direction because it makes comparisons much more meaningful. If you just build a sliver of an array and you don't account for the data movement from your weight memories and so on, it's very easy to get high efficiency, but really you have to account for the entire data movement to know what happens at the application level. We made a very simple VGG-like neural network at the time. There weren't any fancy architectures, and we weren't smart enough to use 3x3 filters at the time. We used 2x2 to make things compact. Really, we should have done 3x3, which would have also been possible, and we lost some performance by this. But one of the downsides also is that we made these regular, so that's what's meant by VGG-like. Nowadays, these kernel sizes, they want to vary from layer to layer. But anyway, this is sort of what we had. And the performance was actually quite nice. And at the time, there wasn't much to compare against. If you go, of course, to GPUs and FPGAs, obviously, they are much less efficient when we build a custom chip because specialization always gives you energy efficiency. So just to point out here, this is about 4 microjoules per inference, and the inference accuracy on CIFAR, which is a medium complexity task, not extremely difficult. It was 86%, and we're really limited by these 2x2 kernels. People routinely get close to these 94% human accuracy with 3x3 kernels. We then went on, and you know, this was the interesting part of this project. We did a fully digital version as well, just to see, hey, you know, what if we kept the same principle, the same weight stationary architecture, and we just toss out this analog accumulation, what would happen? Well, it turns out the digital solution was actually pretty close. Within a factor of 3 or something like this. And that is simply because single bit accumulation is also not so difficult for digital. So you replace this charge accumulation wire with a digital pop count, and it didn't really add too much. And so that was an interesting learning. Obviously, this is good, but a lot of the goodness of this just came from specialization and making this weight stationary data flow for this particular application. So a little more modern comparison now. In particular, Intel just showed a BinaryNet accelerator in 10 nanometer CMOS at the last VLSI symposium, and they also use almost exactly our weight stationary architecture to do this. And so now you see, so this is our energy efficiency in TOPS per watt at the array level. So this is just the compute array, not the full chip. It's a few hundred TOPS per watt. Compare that to a fully digital solution that obviously has 8 bits here, which you can't really compare, but I'm doing it anyway. Obviously, 8 bits will be much less efficient, but this is just to show you the range. But more importantly, this 10 nanometer fully digital design that also does single bit not only achieves the same, roughly the same compute efficiency, but it's also a lot more dense. So on the x-axis here is the TOPS per millimeter square. So it's more dense for one because it's 10 nanometer, but not only that, it's dense because it's digital. So our analog stuff with these big capacitors and these gates and so on, it's just not as small as logic. So when you look at this, what would you say? You say, well, you know, this was kind of cute, but we need to do something a bit more meaningful because clearly the digital folks, they're killing us. I mean, they can do 8 bits. Reasonably efficient, they can do 1 bit, much more dense, similar efficiency, and so on. So to push this concept ahead, really, we need to investigate what higher bit widths would do for us, and we desperately have to reduce the size of these compute elements so that we can move to the right. So we are now working on a multi-bit version of this concept, and it is, of course, possible to do multi-bit mixed signal multiplication. Here's just one way to do it. This is a simple unsigned cartoon. You can also do a signed version. If you pay attention, this actually looks a lot like a normal multiplier. In a digital multiplier, your first rank are these AND gates. And then after that, you sum up the partial products. And the summation of the partial products is done here in the charge domain, not only within each unit element, but between each unit element. So you have now here 5 wires for this 3-bit multiplication. And these are basically binary weighted, and you can combine them into one accumulation result that can be digitized. So this is actually a way to make a multiplier much more compact than a digital one and keep these unit sizes still relatively small. These combiners, by the way, they can be integrated with the ADC, which anyway tend to have binary weighted input networks and so on. So there's a little bit of design creativity you can do. So when you study these things, and you know, we've made a little bit progress on how you analyze this and what the exact trade-offs are. One of the issues you have with these passive combiners is that the signal swings tend to be very small, especially if you stack up many rows. What is this? Well, this is basically averaging. So if you think about these input activations and the weights as random variables, and you passively average many of them together, you know, your mean approaches, your sample mean approaches the mean, and your standard deviation goes to 0. And so you end up having very small signals here, and that means the noise at this point has to be very small. So either you need to add amplification here, or you need to build higher resolution ADCs to bring the noise down. For example, you may end up needing an 8-bit ADC to do 4-bit quantization at this point. So I've done some detailed analysis to this in a paper that will come out pretty soon. And this actually gives you a feel for, you know, given all these trade-offs and noise and so on, what makes sense in terms of operand bit width for this mixed signal business. And so this black curve is basically the answer. If you're in the region of 2 to 4 bits or so, you can get by with single-digit femtojoule per Mach. And this is because thermal noise is not hitting you very hard yet. However, if you crank the dial and you want to do 8-bit arithmetic, the signals become extremely small. You need to amplify them, or you need to build sensitive ADCs. And now you're really starting to see this thermal noise asymptote, which is a slope of 4x per bit in the noise-limited regimes. And so the crossover between mixed signal and digital, just from a computation perspective in my mind, is exactly somewhere around there. If I want to do 8-bit analog and I want to build a large array, I'm actually very pessimistic that you would ever beat digital compute at that level. And it's obvious that there has to be a crossover somewhere. The question is just where. And so to me, this mixed signal stuff makes the most sense down here, where you can sort of retain maybe an order of magnitude in the compute efficiency. And in addition, maybe you can achieve less data movement given the density of your compute elements and so on. Now here is just another version of this plot that I showed previously. Now I overlay these energy levels that I think are reasonable to expect for mixed signal compute. You kind of see they're sort of in line, at least qualitatively. Here we had single bit, and yeah, this may not have been as optimized. So I'm now saying you can do 2 bits a little bit more efficient than we did 1 bit here. But then when you go to 4, 6, 8, so 8 bits, you're starting to touch the state of the art in just vanilla digital. So you may as well build a digital accelerator and optimize it. So let's now go on the next axis, so density. So again, we recognize that this is not the most area efficiency implementation. And so people have meanwhile come and really sort of pushed this in the direction of in-memory computing, as it's called. But the idea is actually the same. You build maybe one local weight storage element, which is an SRAM cell in this case. And then you use capacitors to charge share between rows and between cells in adjacent rows. So this is essentially going from a huge area here normalized to F square, minimum feature size square, 24,000 to 290. So this is like 100x smaller. And this is of course very welcome, because now you can even build larger arrays, you can amortize better, and so on. So this has been pushed now also in the direction of complete processors that my colleague Naveen Verma and others have built. So they have a complete flow, they have everything included on this chip with all the memory, external DRAM, and so on. And at the core of it is this array with ADCs. And so the way they built this is also kind of interesting. They made it reconfigurable in terms of bit width. So each unit element is a 1-bit compute cell, but you can do multi-bit by essentially serializing the data through these cells. So instead of computing parallel, as I showed in my mixed signal array previously, you can serially push this data in and you distribute the weights between the columns. So now, of course, you have more A to D conversions. You have to push more A to D conversions through this. But if your array is big enough, that could actually be fine. And so here they claim that the ADC is only 15% of the energy. And this is probably correct, because look, this N is 2,300. They have a lot of rows. And so this overhead is enabled by having a very large number of rows. So now when you serialize, it turns out the penalty for multi-bit is linear in the number of wait bits and input activation bits. So if you increase them one by one together, it's actually a quadratic penalty. And so this actually means that the efficiency of such an array also deteriorates very quickly as you go towards higher bit widths. So I illustrated this here in this plot. This array is extremely efficient for single bit. That's what this bar is here. By the way, each of these points is just 2 different supply voltages. And this is very close to what we achieved for single bit, and this is not too surprising. I mean, this is essentially the same idea, the same architecture. The switching is done a little bit differently. That gives them a small penalty, but this is not surprising. But then when you go to 2 bits, it degrades 3, 4, 5, 6, 7, 8. And so at the 8-bit level, it's actually, again, quite questionable whether you can compete with digital. Now, this data is for 65 nanometers. This is for 16, so it's not fair. So you can definitely argue, well, this should go up maybe somewhat linearly or so with process. Maybe you can gain factor of 4. Maybe you can move this to the right, but you can kind of see what to expect. So if I did a really good job scaling this to 16, maybe I would be left with an advantage of 3 or 4 over this digital design if I wanted to at the 8-bit level. So really, again, in my opinion, if you want this mixed signal stuff to fly, it's probably better to shoot for the lower bit widths. Now, how about pushing this into a much more aggressive direction now, and in fact, try to eliminate more of the data movement energy that I haven't even talked about. So if you have a very efficient array that clearly helps you energetically, it may also help you reduce the data movement from the higher memory layers. But what if you wouldn't even have to bring in memory from off-chip, bits from off-chip and so on? And so this is something many people have been talking about. There's emerging memory that promises to be ultra dense. So what if you could put a billion parameter deep neural network on a chip, maybe in a 3D memory that talks directly to the compute underneath and so on? So this is a very interesting vision, and many different memory technologies are possible. I will talk about here about resistive RAM that has programmable resistors. You can also call these memristors. And essentially the idea is to say, well, you know, SRAM is nice and dense, but you can actually be even denser. So these RRAM cells, at least in the limit, promise to go down in area to as low as 12F squared. And you may be able to program these resistors to multi-bits, and maybe 2, 3 bits is enough in terms of weights. And now, instead of summing charges, you are just summing currents. So you're basically using KCL to do accumulation. So this is, of course, not something I invented. This idea has been around for a very long time, and many people are working on it. But I want to highlight some of the things that we focus on. So we want to build relatively large arrays in my group that can actually handle an entire DNN layer. So if you have a DNN layer that, for example, has 1 megabyte of weights, can we store that entire megabyte in an array and then do all the computation essentially in one clock cycle? And what's nice about this is if you could actually do this, and if these cells are relatively small, you could lay out the entire neural network on your chip and just pipeline the operation through this. So you would have small SRAM line buffers that basically keep the RRAM busy, but these SRAMs would be very small because they just hold the current working set. They're just basically there to establish communication between the different in-memory processing units, and the whole thing would look more like this. So this is a drawing taken from some researchers at IBM and ETH Zurich. So this is a ResNet where you have an array dedicated to each layer. You see here the residual connections, and this would be very interesting. And again, the external memory is gone. All the weights would be stationary. There would be no energy dissipated in moving any weights, and the activation movement is also very limited, or doesn't hit large memories in between because it's of the pipeline operation. So a key aspect here again is then D to A and A to D, because that still stays as a bottleneck. How do you efficiently digitize? How do you efficiently get multi-bit activations into these? So The old school thinking is to put a transimpedance amplifier on these bit lines that take the currents, basically this accumulation. But that ends up being very power hungry. Imagine having an array that's maybe a few thousand cells tall, trying to make a virtual ground and maintaining reasonably low noise with a TIA turns out to be very power hungry. Not only that, also allowing the voltage drop across these resistors is power hungry. It's actually not too easy to make these resistors much larger than 100K. And if you had 1 volt across them during read for say 10 nanoseconds, this is the types of speeds you get out of large arrays, you would already burn 50 femtojoule per operation just by heating up that resistor. So not anywhere near the 1 femtojoule that I want. And so this clearly shows in some of the publications that really don't get off the ground very much. They're in the tens of tops per watt. So we've been looking at a different idea. So instead of trying to build a TIA-like structure that senses the current and dissipates static power, so to say, on these resistors, how about doing something more dynamic? Precharge the bit lines as you do in a DRAM or an SRAM, and then let these resistors discharge the intrinsic or the parasitic capacitance of the bit line. And that should now be somehow dependent on the weights and the activations. So where the activations are applied at the gate in this case. So how does this work? So first of all, let's see how we would bring in the input activations. So the input activations in this case actually hit the gates. And if you want multiple bits, you could serialize it or you could do it in parallel. We decided to do some parallelization. So this is very similar to the concept of Naveen Verma's, except here it's applied to the rows. So we use two rows for an MSB and 1 row for an LSB. So this is single bit, and then this expands it to 2 bits. So this is how we bring in multi-bit activations of 2 bits. And then for to encode, we have pulses on these activations. And so now it's actually interesting to solve exactly what does this transient waveform look like. So when you apply a pulse here and let this network relax, how does the voltage depend on the dot product that you want to compute? So it turns out that a hyperbolic sinusoid shows up. This is interesting. You can figure this out by just doing the network equations on this. But what's interesting is that inside this hyperbolic sine, you actually have the desired dot product. So we looked at this and we said, wow, this is interesting. We could actually train the neural network to get by with this hyperbolic sine and just work with that. So fine, you know, this should all be very easy and it should be nice. But what we found is that the reality isn't quite as pretty. So the simple model that we assumed in deriving this hyperbolic sine has a switch and a capacitor and everything is very pretty. Once we get our hands on real RRAM cells, they look more like this. There's a billion coupling caps. These things are very tight. Everything couples to everything else. And so the settling waveforms are incredibly ugly. So instead of settling very nicely to the desired value that we want, this is this red curve here, depending on what you model, you get vastly different waveforms. And after we saw this, we knew that, well, there's really no way that this would work if we did this in reality. So, but given that we really like this dynamic operation, what can we do? So we came up with an alternative idea that basically says, well, if the operation on the bit lines is nonlinear and somehow non-linearly dependent on these parasitics, why don't we do something that is well understood, a ramp-like or kind of linear approximation-based A to D conversion? So the idea is actually conceptually very simple. Instead of measuring the value on the bit lines, we're trying to force it to 0 with a quantity that we ramp up. So we're letting this array settle, and as we do this, we apply different values that try to null this. And when you null this, when you always get close to the nulling point, the nonlinear components are basically mitigated. And so the structure that we can build for this has the usual weights and the bias. And then in the bottom, we extend the array with extra cells. And these cells are merely there to null the voltages. And so we try one combination, we try another, and we try another. And for 2 bits, this is not too bad. You just have to do 2, 3 trials, and you have found the right output, and then you just need a comparator here. So you can think of this as an A to D converter that nulls the bit lines using ramp cells here that are a replica of the overall array. So you would basically pre-charge, evaluate, pre-charge, evaluate, pre-charge, evaluate. And this looks very inefficient, but it turns out that when you evaluate and you find that you just crossed the 0, you can skip the later steps. And so energetically, you actually gain quite a bit from this, and you exploit sparsity and so on, all of these good things that are happening in neural networks. So we put this to the test. We put together a neural network, a small one, VGG7, 4.8 million parameters, a few layers. And so this is a simulation only. 2-bit activations, we have 5-level weights. So not 5-bit, but 5 levels. So this is 2-point-some bits. And that was trained to get around 93% accuracy on CIFAR-10 if everything is ideal. And the way these kernels work out, you have 3 by 3 by 128. If you multiply this out, the largest kernel would have 3,856 RRAMs cells per column. 5 conductance levels, there's not much of an interesting detail here, but this is sort of typical values that the technologies we use have. And so we have 5 levels for symmetry mainly. So now the interesting part is when you study the circuit nonidealities, you have to assign some sigmas to these conductance values. The comparator will have some noise. And so we did extensive training to see how much can be tolerated. And so this leads to this Shmoo plot here. So let's look on the left side. So on the x-axis is comparator noise, where each increment is about 170 microvolts added. And on the y-axis is the sigma of the unit conductance. And so obviously this is the best point, upper left. So this is this 94%, close to 94% accuracy. And then it degrades. And so this point that I marked, you have about 25% sigma in the conductance variation and 1 millivolt a comparator offset and noise. So this gives you, this sort of parks you somewhere where the error degradation is at the verge of decreasing by about 1%. So this really would have to be decided at the application level. So when you look at what this prototype achieves, and of course this is just SPICE simulation, it's post layout, and it's only array level. There's no overhead factored in at all, but it gives you a feel for how dense these circuits are. The density would be very high. So for 2-bit weights and 2-bit activations, this is for a 40 nanometer technology. It is as dense as this single bit 10 nanometer design. And the compute accuracy is again somewhere in this single digit femtojoule per op, or in other words, a few hundred tops per watt that we can get out of this. So this is very promising. The challenge now lies in actually building this and actually building a convincing system. So far, people have mainly demonstrated very small arrays. They emulate the network with a lot of software around these emerging memories. And so the benchmarking is actually quite difficult until you really build all the interfaces and you figure out what all the problems are and the variabilities and so on. But I will certainly keep pushing at this front. It's an interesting direction, especially if you believe in these emerging memory technologies in the long run, and expect 3D integration and so on to happen. I think at some point we will certainly embrace ideas like this. So after all of this, sort of my main perspective is mixed signal. Is it worth it or not? I think the jury is still out. In some cases, especially if you had very advanced technologies, it may become a no-brainer in 10 years from now to do this. But for the time being, the question you need to ask as someone who makes money selling these chips is, if you can get 5 to 10x improvement from these mixed signal and in-memory architectures, is it worth the loss of generality or flexibility? So there's this undeniable little bit of loss of flexibility that you lose over digital. I mean, digital is constructed to be extremely flexible. Even for DNN accelerators, they can handle a lot of different types of networks and remain reasonably efficient. Whereas in these mixed signals, the efficiency comes from really having the kernel sizes right, and so on. And so this is sort of what we need to answer. So how flexible can we make these mixed signal architectures? So a lot of work should actually go into pushing these points further to the right and somehow try to maintain the efficiency. As we do that, it's also important really to consider new network architectures. There's a lot of stuff happening in network optimization. Here you see an example. MobileNet V2 actually uses quite different convolutions. They have these bottleneck layers where you come in with a relatively skinny volume, and then you do an expansion into a higher dimensional space. And within that high dimensional space, you do very small kernels, 3 by 3 by 1, which are best done digital. And then you go back and do a projection back into the compact space. And for projecting into the space, expanding into the high dimension space and projecting back, mixed signal would be interesting, while within that space using the small kernel will probably have to be digital. So we would have to come up with architectures that really allow for these new emerging, these will constantly change. Their sizes will be different from layer to layer. How do we deal with this efficiently in mixed signal architectures? So this is my conclusion. So I've been dabbling in this space for a few years, and I still truly believe that mixed signal compute offers an interesting degree of freedom that you don't have in digital, simply because you can have these dense weight stationary processing elements that give you a very efficient means for accumulation that is just very hard to do in digital. You can certainly accumulate in digital, but it costs you either with memory access or forming pop counts and so on, reduction trees and so on. The challenges though, and this is kind of where everything will be decided in the end, is can we maintain a reasonable amount of flexibility, get good utilization as the kernel sizes vary across the network, managing all these noise and mismatch requirements, building dense circuits. So if anyone has designed an interface to an RRAM, you will know how tough it is to match these pitches of the RRAM. In fact, you usually can't. You have to fan out into wider, into multi-pitch structures. The denser this stuff comes, the more difficult it gets to interface to it. And then on top of this, these emerging memories, there's a lot of subtle issues with variability, retention, endurance that you have to deal with. Lastly, I want to point out, and this is something that I'm getting more and more interested in, there's still an absence of really system level evaluation of these mixed signal approaches in a good simulation framework. So how does the data actually move when you have these dense compute arrays? What happens at the higher memory layers? What is the total energy? How should you size this? Should you have multiple arrays? What is the exact configuration? Us mixed signal people often don't go much beyond building a little array and claiming outrageous efficiencies, but we really have to take a more system approach to actually demonstrate what this would look like in the real world. And I think this is sort of ongoing now, and we'll see results out of this coming pretty soon. Well, thanks everyone for listening. I'm obviously very happy to answer questions at this point.
So I suggest that we will have the question via the participants. You can raise your hand.
Okay.
Anyone?
There should be some icebreaker. I know you guys will have a lot of questions. I've been to Haifa before.
If not, I have many questions. I'm
very
happy that you moved to the memory store business.
Yes. Go ahead, Shah.
So first question, why do you go to 1P, 1R and not a pure crossbar in the resistive RAM? Well,
it's the programming, right? I mean, that's one reason. The other reason is that's what I get from the fab, right? So if I go to TSMC or somebody like this, this is what they give me. They don't give me a crossbar right now. I guess if you make your own, you can make a crossbar, and then you have to sort of figure out how you program that.
So your resistive RAM is from TSMC, not from Philip Wang?
Yeah, it's not from Philip Wang, no. Philip Wang wouldn't give me enough density.
Yeah.
Yeah.
So what is the size of the arrays that you are using?
Say that again?
What is the size of the arrays?
Oh, yeah. Well, I can't say we're using an array yet. We're still designing this. So our dream would be to have a few thousand rows. So, you know, a few thousand by few thousand. But it turns out that is not exactly feasible because of parasitics and so on. So it's probably, it will be a structure that is an array that has a certain amount of subarrays and repeaters on the word lines and things like that. But generally, think about 1,000 by 1,000 type arrays is what we want.
And then another issue will be, since you can't put a single layer on a single array, that you need to move between the arrays, right?
Yeah, so this is handled with this pipelining architecture, right? So maybe I can go back to this. So the idea would really be to have one array for one layer, and then you pipeline them together, and then in between, yes, you need some SRAM buffers, but they are very small because they are just the current working set, right? So you need to make many computations with each array, and you just have partial data in these SRAMs. They're actually extremely small, maybe 1,000 times smaller than the RRAM.
And a more general question, what about training with mixed signal?
Yeah, so I get stuck here. So the conventional approach, right, these normal neural networks, they need sort of 8-bit floats to be trained, right? I mean, this is the best I have seen from the IBM folks. Now, if you go away into a more neuromorphic type architecture, right, there's other ways to train without high resolution. And then you can probably do training with mixed signal as well. But I have not explored that at all.
Any other questions? Okay, if not, then...
Oh, there is someone, Tsai.
Tsahi? I don't... okay.
Yeah, please go ahead.
Tsahi, you are unmuted.
Now I'm unmuted. Yeah, there were no questions because you muted everyone. So that I think was part of the explanation. For the inference, where are the weights stored?
Which architecture are you referring to?
Well, the one that you use as your best.
Well, so the weights would be stored in the compute array, right? So
yes, but are they stored analog or digital?
Well, okay. So in this architecture, in the first set of architectures, they would be stored digital, right? Okay. Like in this SRAM approach. Mm-hmm. For example, it's just the 6T SRAM cell, right, that holds the weight bit. Now
Okay.
in the RRAM, it's stored as the resistance value. So you could call that an analog weight.
Yes, okay, so my question refers to that. What happens with repeatability? Let's say that I trained whatever way I trained, and now I want to have 1,000 chips that all have the same weights, resistance, analog. How do I adjust it? How do I make them close to what I really want?
Right. So the weights are not programmed during manufacturing, right? So there's a programming step. So these RRAM cells, they first need to be formed. You first need to break the oxide. And then during programming, there's actually a write, read, verify scheme. So you basically program a resistance value, then you measure it, and if it's off, you program again. So programming these cells is actually a bit elaborate, but the nice thing is potentially you have to do it only once, right? So
once per algorithm.
Once per algorithm, yes.
Yeah, because this, I mean, the first time you can do in the fab or in some step over there, which would be akin, I guess, to spending tester time.
Exactly.
Similar kind of thing, expensive equipment being used individually per chip to adjust it. But then,
yeah, I mean, honestly, this is a more general problem with these emerging technologies, not just limited to my application. In fact, testing and programming of these emerging memories is a beast. But yeah, you're right. I mean, there are interesting ideas out there, like extreme learning or whatever you want to call it, where you actually initialize some of the weights randomly and you just program the later layers and things like that. So there may be some games where you can save some write access to these weights, but you're totally right that this is one of the big overheads, right? Programming all these weights is a mess. It'll take a long time. It takes a lot of energy, but the point is, yeah, if you have one application and you only need to do that once, maybe it can be okay.
Yeah, so I mean, let's say I have an application, FBI looking for a suspect. And the suspect changes. I want to load a new guy, and I feed in whatever video or images of pictures of crowds or what have you. But whenever I need to change suspect, I'm really changing the algorithm, let's call it. I need to reprogram the weights. So even if I have them ready, I need to bring them in somehow.
Yeah. So, if I was looking for suspects, I would do the computations in floating point on a server. I honestly, so maybe we can talk a little bit about the applications. I didn't really go much into this. I think this is kind of consumer applications. If you have your doorbell camera or something, and your objective is really to get the lowest possible energy and the lowest price for that chip maybe, or these are not really defining the high end in machine learning capabilities. And these applications, right, I mean, so I'm getting back to my point at the end, they're not going to offer the same flexibility as digital, right? So when you go back to this chart, life is a big Pareto curve. If you want to be efficient, you're probably not going to be as flexible as some other alternatives. And that's the trade-off. I mean, if someone tells you they have simultaneously the most efficient and most flexible thing, that usually doesn't exist. So
yeah. Okay, and another thing that could be interesting, suppose you have some kind of doorbell or whatever, and what you want to do is recognize whether it's your dog ringing. It's the same dog all the time, so forget the previous problem I raised. But now it's a very sparse thing, because usually the doorbell isn't ringing. Or you could have a very, very, very simple activation circuit that normally keeps everything off. It only turns it on when there's something.
Yeah.
And then the efficiency, the energy efficiency of this is less important, because it's 99.999% of the time zero energy, or just the activation. So it's an interesting answer, looking for the right, I mean, I'm sure there are right questions for it.
Yeah, well, so you're right. You're totally right. So the doorbell problem would actually be solved within hierarchical classifier. You would actually have a cascade of algorithms. You would first have a wake-up network, and that network wakes up a bigger brother, right? And we have done these as well. And yeah, these are much simpler. In fact, they may not even be a neural net. They may be based on a support vector machine or something like this, something much simpler. And then you wake up this one. Well, at the end, this actually still matters even in the doorbell, but because it's the energy, you know, you want these batteries to last for several years. And so it's really about how much energy you accumulate. And if you can make this wake-up circuit really, really efficient, and even then, you have a certain duty cycle. You know, the tree is shaking in front of your house. So, you know, even I can tell you that even the people who do the doorbells, they do want efficient CNNs in the back.
Okay.
Yeah, yeah. But you're having exactly the right thoughts. Yeah. Yeah.
Okay, Leonid, you are unmuted.
Hi, thank you. So the question is, and I'm not sure if Tycho already asked it. So if you listen to Bill Daly, he will tell you that arithmetics is free and data transfer is what it's all about. So I'm just wondering, is it possible that we are trying to optimize this 1% while, you know, 99% remains unoptimized or maybe even unattended?
Well, so I thought I addressed that in the beginning, but let me talk about this again.
Yes, yes.
I fully agree with that statement. Convolutional neural networks are all about data movement. And you see that, so let's go back to this picture actually. So in the end, most of the energy is consumed by moving data between all these memory levels. But you have to keep in mind that the way you compute also affects the data movement. I think this is what most people don't understand. So the Bill Daly argument is kind of interesting. He says, well, look at this chart. Even if I make the compute 0, right, if I cut out this blue 31%, nothing happens, right? Nobody cares. And so he goes home and he says, no one should ever talk about compute. Well, in my mind, this is a little bit superficial, because what if the way you compute had an impact on how much data movement you have?
Right.
So this is the whole point. So if I can build a system that has more parallelism and less data access in this bottom array, then I may be stressing the higher levels also less, because I can have much more local caching. I have better data stationarity in this array, and so on. So the two things are joined by the hip. You cannot say orthogonal, compute and memory data movement is orthogonal. They have a huge impact of each other. If what Bill says is 100% true, then why do you even build a vector MAC? Just build one MAC. If compute doesn't matter, why do you even do vector processing, right? So what I'm saying, make this much more parallel so that you consume and reuse data much more efficiently.
Thank you.
Yeah. And to be honest, it's still not going to be many orders of magnitude. This is where my factor of 5 comes in at the end, right? It's not turning water into wine. It's just, I think it gives us a little bit of a flexibility.
Any other questions? Okay, if not, then both, thank you very much. And we hope to see you next time in Israel.
Yeah, hope to visit. Be fun.
Yeah, thank you. It was great.
Thank you, everybody.
Bye-bye.